Imagine two distinct trails winding through a forest, each walked by a different fox. Eventually, those two paths cross. That specific clearing is the one location that exists on both trails at the exact same time. In algebra, when we track two different relationships to find where they cross, we call it solving a system of equations. Let's look at the mathematical paths for our foxes. We have the equations y equals x plus 2 and y equals 10 minus x. Because the paths cross at the exact same location, the y values at that spot must be identical. That means the expressions defining y have to be equal to each other. To solve the system, we just need to find the specific ordered pair, the exact x and y coordinates, that makes both relationships true at the same time. We start finding that intersection point by setting the two expressions equal to each other. So we write x plus 2 equals 10 minus x. Let's group our variables. If we add x to both sides, the right side simplifies down to just 10. Next, we isolate x. Subtracting 2 from both sides leaves us with 2x equals 8. Divide by 2, and we find that our x-coordinate is exactly 4. To find the y-coordinate, we substitute that 4 back into our original equation. 4 plus 2 gives us a y value of 6. That makes our crossing point the ordered pair 4, 6. This substitution method works because it temporarily turns two equations into one manageable equation, all while keeping that shared intersection point intact. Sometimes we want to estimate where paths intersect before we dive into the algebra. This graph plots two new intersecting rivers for our heron, the lines y equals 2x plus 1 and y equals negative x plus 7. We can look closely at the exact spot where these two lines cross. Tracking down to the x-axis gives us 2, and looking across to the y-axis gives us 5. A graph gives us a quick visual estimate of a system solution, which we can always verify later with algebraic steps. Now, let's look at a scenario where the equations aren't neatly solved for y. Here are the equations representing the logs our otters are sitting on. 2x plus y equals 11, and 2x minus y equals 5. Because the x and y terms line up perfectly, we can use a new strategy, subtracting one entire equation from the other to eliminate a variable. Look closely at the stacked variables. If we subtract the bottom equation from the top equation, which variable will disappear? Recognizing this kind of structural symmetry helps us see exactly when elimination is the most efficient choice. If you subtract the bottom equation, the x terms disappear. 2x minus 2x is 0. Be careful with the y terms. Y minus negative y is the same as y plus y, which gives us 2y. Finish up with the constants on the right. 11 minus 5 leaves us with 6, forming the simplified equation 2y equals 6. Divide by 2, and we get y equals 3. Now we just substitute that 3 back into our first equation. 2x plus 3 equals 11, so 2x equals 8, which means x equals 4. That makes the exact interception point for our otters the coordinate pair 4, 3. Just like substitution, elimination preserves the correct intersection point by safely removing one unknown temporarily. We've walked through 3 different ways to find an intersection: substitution, graphing, and elimination. Regardless of the method you choose or the specific paths involved, the objective remains exactly the same. The solution to a system of equations is the ordered pair that makes both equations true at the exact same time. So next time you see lines crossing on a page, ask yourself, what do those intersection coordinates measure in the real world?